And we are live. Alrighty. Welcome, ladies and gentlemen, to the next installment of me, the Mathematically Expedient Modeling Exposition. This initial series will be about differential equations made easy, or Ds for short. And today we're going to be talking about two different sections relating to common types of derivatives that will show up in physically inspired models. So the first section will be about different time derivatives that can be used in spatial modeling. And then the second part will be about conservation laws, which are very common when describing physical models. So first we have different time derivatives. So why do we have different time derivatives? So when you have a model, things will move about, both time and in space. Now, a lot of models work with just ordinary time derivatives, but sometimes we want to account for the changes in the motion and separate that out from changes due to motion versus changes in the intrinsic material in itself. And we'll go over some, in the second part, we'll talk about sort of an example of how that might change. These different derivatives basically account for the different ways that things can change in an extrinsic fashion. They can broadly be thought of in two categories. So there's the Eulerian frame, which is a frame relative to a broad observation, versus a Lagrangian frame, which is relative to an object. And a lot of these are derived via the chain rule and accounting for different interactions and changes between the different coordinates. So as an example, if we have a cloud model, there are two ways we can think about it. The man in the orange riding the cloud would describe the clouds using a Lagrangian framework. So water comes in, water comes out, cloud rises, cloud falls, but it's always from the perspective of the cloud. Whereas the man in the yellow or the beige or whatever you want to call that, I guess it's a little more beige than yellow, would describe the cloud in an Eulerian framework. The cloud can move up and down relative to his coordinate system. It can move left to right in his coordinate system, north and south, all those directions. And it's important to account for these differences in different ways. So the simplest derivative is the ordinary derivative. This is the one that everyone knows and loves. dA dt, partial a, partial t, what have you. This is generally used in Lagrangian contexts when we're just tracking things and we're seeing how things change as it moves about. There's only a dependence upon the time. Right, and this differs, though, from the next derivative, the material derivative. Now, the material derivative looks at a fixed point in space, and it accounts for the motion of an object from a background velocity field. And the idea that for this comes is that if you have some quantity A, which depends on x, which is in itself depends on t, so x, if you have something that depends on x on t, if you want to properly take the derivative with respect to time, you have to apply the chain rule. You have to take the partial derivative with respect to time, and then you have to take apply the chain rule to the different spatial components. The derivatives with respect to those spatial components form the gradient, whereas, and then dx dt is sort of that second part towards the chain rule, and that is equivalent to velocity. And so what we end up with is we end up with partial a, partial t, plus velocity dotted with the gradient of a. Similarly, there is the lower convected derivative, where instead of just things moving about in space, we have that again, that velocity dot gradient a term. We also have a coordinate system now which can deform and rotate due to this fluid flow itself. And so we have to account for how the velocity field changes in space, which is done with the tensor A. The idea here, I don't show the entire proof, but the idea is that the coordinate system, x, is based on some initial coordinate system A, which also changes in time. And if you do all the accounting for that, you're going to get back to your original system. So you take it's noted here that A is in bold, which is for some tensor A. Generically, it needs to be of rank. Well, has to be of rank 2, I believe. Yeah, so this is the lower convected derivative, handles tensors and how the tensors can deform within space. There is also a upper convected derivative. It is similar to the lower convected derivative. However, this operates, there's a minus sign leading up to the latter terms, and that handles contravariant tensors. So in tensor mechanics, you have covariant and contravariant tensors. Covariant tensors, if you change, so all of these depend on a basis of vectors. So if the basis of vectors changes, things that change with the vectors, so if a vector gets longer, if the secondary quantity gets longer as a result, that is called a covariant tensor. If it shrinks as a basis vector gets longer, it is called a contravariant tensor. Both of them are fairly common, but it's important to track the differences between the two, especially when using convected derivatives like this. Finally, we have a corotational derivative. This applies to certain tensor fields when there is deformation, but there is no rotation. And we do that by accounting for basically the vorticity tensor, which basically takes the gradient of a velocity vector and its transpose and subtracts the difference. The components are the different components of a curl, but just in tensor form. Right. But generally, though, these are fairly straightforward and simple. If you have, and if you want to know which ones to use when, if you have a Lagrangian framework for your model, you just use an ordinary derivative. If the motion only changes with the location of a material, you want to use the material derivative. And if you have some more fancy, complicated situation, then you're going to want to use some fancier derivative. Now, what the appropriate fancy derivatives are going to be very model dependent and something you'll need to take care of. However, usually when you get to that point, you're already busting open some fairly fancy calculus. And so at that point, I would just say look into the books and look at the literature to see what the appropriate derivative choice is. So with that preface out of the way, we can move on to the main meat of the second lecture, which is conservation laws. Conservation laws are very common. If you've ever heard of like different conservation laws out of physics, you have conservation of mass, conservation of energy, conservations of momentum, things like that. There are a lot of models will have some sort of conserved quantity, and even if quantity is not precisely conserved, oftentimes we can track how new elements of this quantity are introduced. And I'll go over an example of both of those during the lecture. So if we want to understand where these conservation laws come from, suppose we have some quantity f whose movement is dictated by some vector field f of z. And the amount of z in a volume changes with time. So we take a volume integral of z, and we take a derivative with respect to time. If we have a fixed volume, the amount within that integral, as it changes with respect to time, must be equal to the amount flowing out of the boundary of this volume. So if something is leaving it, we have to keep track. So the only way something will change is if it leaves through the boundary. And the stuff that leaves through this boundary is captured by the cyan integral, which is a surface integral of that flow field up against a normal vector. And if we equate the two, we get an initial equation, ddt of the volume integral is equal to this surface integral. Now, if we have a divergence theorem, if we apply a divergence theorem to that surface integral, what we get back is we get a similar volume integral. And what we can then do is we can then combine the two volume integrals into a single integral equation. And if that holds for any volume v, we can get a conservation law. dx dt plus the gradient of f with respect to x is equal to 0. This is a fairly common thing, and we'll go over an example in a moment. But a similar idea happens with the Reynolds transport theorem. It is a similar idea where you have a time-dependent volume which moves with velocity v sub b. There is a similar surface integral that emerges. We can then apply a similar divergence theorem to it. And when we combine that to when we apply that to the earlier integral, we can find that the change in that quantity z with this change in volume is equal to a material derivative plus the quantity times a divergence term. So if you ever see a model where it's talking about where the divergence of a velocity field is important, this sort of explains why. The cyan term sort of says, hey, so if there's a material derivative of z, but anything else, but we can also see additional terms being created by this z times divergence term. Now, there are a number of different flows that can exist. So f can depend on the situation, how that velocity field is generated can be dependent upon a situation. The most common example, though, is a gradient flow. A gradient flow is basically if you have some quantity xz, stuff flows away from where xz is the largest, and this will produce in the direction of greatest growth or greatest decrease, greatest increase is that gradient. And that gradient can be modulated by some sort of spatial variable alpha sub x, so I include it here. And in doing so, we get a continuity equation, dx dt is equal to the divergence of alpha gradient xz. And this is what we call a diffusion equation. These are super common in material sciences. The most famous version is the heat equation, where that alpha x term is just equal to 1. So we have dx dt is equal to a Laplacian of xz. These are super popular all over the place. Heck, I've even heard cases where it will show up in like machine learning applications where you hear about like diffusion. I'm pretty sure that is the same diffusion process that we're talking here, though over a more discretized version. This is super ubiquitous. So hopefully that explanation makes sense of why diffusion shows up all over the place. It's a thing flowing away from itself, basically. There are also non-conservative terms, though, right? We have conservation laws, but not everything is perfectly conservative. So what we have here are the Euler equations for a fluid. And what the following equations describe, basically, are how the mass, momentum, and energy are conserved on the left, but on the right of each of these equations, we have a non-conservative term. So if we look at that first cyan mass equation, we see that there's no way for new mass to be generated in a normal fluid. And that holds true, right? You can't really create and destroy mass in a normal fluid. Momentum, on the other hand, can be modified. So we have like a pressure terms and we have advective terms showing up in the purple terms. However, we can also introduce momentum by introducing a force, right? If we have some external force, we can generate new momentum. And similarly, an external force, if it's moving in the same direction as a velocity, can increase the energy in an equation, right? But these are external sources of momentum and external sources of energy. It goes into the system from something outside of it. And this is important. It allows us basically to keep track of how things are coming in. And oftentimes, when solving and developing new models, you can turn these things on and off. So like, you can say, oh, there are no external forces. And then you have a purely conservative system. And you can do all sorts of fun analysis on that. Or you could turn those forces off and then come up with some new manner of generating mass, like some weird like particle experiment or something. I don't know. Right? You could if you wanted to, at the very least. And then finally, though, even larger systems of equations have conserved quantities within them. So if we consider the Maxwell equations for electricity magnetism, we have them out here. We have Gauss's laws for electricity magnetism. We have Ampere's law, and we have Faraday's law. And then there's the Maxwell addition of the dE dt term. Right? If we take that red term, what happens is the green term drops out. What we see is we have a divergence of J plus a time derivative of the divergence of E. And the divergence of E, as we know from Gauss's law of electricity, is proportional to the electric charge density. And so if we apply that, we're going to get this conservative equation. Basically, the change in the charge density with respect to time is going to be proportional to the divergence of the electric current density. And this makes sense. If you have more current coming into a thing than leaving it, you're going to get a buildup of charge. If you have more current leaving a thing, you're going to get a decline in charge. And this is an important mechanism for understanding the basis of how electricity moves. And with that, that ends the main portion of the lecture. However, if there are any questions, please feel free to answer. I'll be on for a few more minutes, but if no one has questions, I will end the stream in relatively short order. Please ask me some questions, or I will quit today. Questions about time derivatives, or the conservation laws that we love. Thank you for watching and subscribing. No, seriously, thank y'all. Unrelated news, or semi-related news for the channel. I got accepted to YouTube partner programs, so if you would ever like to leave a super chat, that is now available. I think, if someone wanted to make my day, they could leave a super chat, and that would leave that I would actually make money, which I've never done, so I think that'd be kind of cool. I mean, I've made money before, let's be clear. I have not made any money on YouTube or posting social media, so that'd be kind of cool. You don't have to, but I don't know. Seems something cool kids do. So anyway, thank you for watching. Make sure to subscribe, like the video, share with some friends, share with some family, share with your math teacher. I don't know. Anyway, have a good day.